At 140 GHz, wireless communication faces extreme propagation losses. Signals alternate quickly, and the transmit power is limited by RF hardware. So, how can we still build reliable links at these frequencies? The answer is beamforming. By combining signals from many antennas, we can create highly directional beams that focus energy toward the receiver. But there are multiple ways to implement beamforming, and each architecture has different trade-offs. In this episode, we'll explore the three main beamforming architectures used in sub-THz systems. At lower frequencies, a single antenna might be sufficient. But at sub-THz frequencies, the link budget becomes extremely challenging. Path loss increases with frequency, while PA output power is limited. Beamforming combines signals from many antennas. If we use N antennas, the array gain increases roughly as 10 log 10N. For example, a 64 element array can provide around 18 dB of gain. In real systems, there are three main beamforming architectures. First, analog beamforming. Simple hardware and lower power, but less flexible. Second, digital beamforming. Much more flexible and powerful, but it needs more hardware and more power. Third, hybrid beamforming. This combines analog and digital techniques to balance performance and complexity. So, in practice, engineers are always balancing three things: hardware complexity, power consumption, and system flexibility. There is no single perfect architecture. The best choice always depends on the system design goals. Let's start with analog beamforming. This is the simplest beamforming architecture. Signals from multiple antennas are combined using RF phase shifters. Each antenna path has a phase control element that helps stir the beam. The main advantage is low power consumption, because the system only needs one RF chain. But there is an important limitation. With analog beamforming, the system can usually create only one beam at a time. So, analog beamforming is simple and efficient, but not very flexible. Now, let's look at digital beamforming. In this architecture, each antenna has its own RF chain, and each signal is converted using its own ADC or DAC. This means every antenna signal is digitized separately. Then the signals are combined and processed in the digital processor. The big advantage is flexibility. Digital beamforming can create multiple beams at the same time. It also enables advanced signal processing and spatial multiplexing. But there is a trade-off. At sub-THz frequencies, this approach requires a lot of hardware and very high power consumption. Digital beamforming is the most flexible approach, but it is also the most complex and power-hungry. Now, let's look at hybrid beamforming. As the name suggests, it combines analog and digital beamforming. Instead of giving every antenna its own RF chain, the system uses a smaller number of RF chains. First, coarse beamforming is done in the RF domain using phase shifters. Then, digital processing is applied across the RF chains to further shape and control the beams. This approach balances flexibility and the hardware complexity. Because of this, hybrid beamforming is widely used in millimeter wave and sub-THz communication systems. In many modern systems, hybrid beamforming offers a practical middle ground between analog and digital beamforming. Each beamforming architecture has its own trade-offs. Analog beamforming is simple and energy efficient, but it has limited flexibility. Digital beamforming gives the highest performance and the most flexibility, but it also needs much more hardware and much more power. Hybrid beamforming sits in the middle. It provides a good balance between performance and complexity, which is why it is widely used in modern systems. In practice, many millimeter wave and sub-THz systems choose hybrid beamforming as the most practical solution. Beamforming is a key technology enabling sub-THz wireless communication. By focusing energy into narrow beams, antenna arrays can overcome extreme path loss at 140 GHz. Different beamforming architectures provide different advantages. Hybrid solutions are currently the most practical, while research continues toward future 6G systems. That's all for this video. Thanks for watching. If you like this series, please like, share, comment, and subscribe.